stability. So first one is gain margin and phase margin. So gain margin is assuming that gain margin is the frequency at which the phase shift is 180. So when you vary the frequency, you find out the gain. So when at what frequency the phase shift of this term becomes minus 180, that frequency is called as that omega pi, and the gain at that particular frequency is called as gain margin. The gain margin now you have to see the phase angle minus 180. Phase margin now you have to see the gain. For phase margin, you see, find the frequency at which the magnitude is 1. Ulta or gain margin, you find the frequency at which the phase angle is minus 180. At that frequency, find out the gain. Phase angle, now find the frequency at which the gain is unity, and at that frequency, find the phase angle using this formula. The gain margin and phase margin are very, very effective methods to determine the stability of your system. So they will clearly give an idea without doing any other test. We can clearly say how gain margin and phase margin can depict the stability of your system. Okay, so that is going to be very, very important. So the diagram is given. Gain margin, you see, minus 180. So at the frequency minus 180, what is the frequency omega pi? At that omega pi, what is the gain? Phase margin ku see where the frequency is 1, dB is 0. So this is the frequency. At this frequency, find out the phase angle. That is your phase margin. So one must choose gain margin as large to accommodate all signal variations. The gain margin has to be large. In most cases, see here, minimum gain margin of 3 to 5 dB is required. But phase margin also has to be large to accommodate all the phase shift variations. So typical phase margin is 30 degree to 60 degrees is acceptable. So gain margin 3 to 5 dB variation in gain, and phase margin is 30 to 60 degrees is the acceptable phase margin. And this range is quite high, but practical case you will start reducing that gain margin and phase margin.